The next mini session is comparing theories of consciousness, and our first presenter is from Chapman University, Kelvin McQueen.
You can hear me okay? Okay. No. How's that? All right, good. So I will try and be quick because I know we're close to finish. Okay, so first of all, I just give a shout out to my co-authors who I've worked with on this project. Markus Müller, who's a physicist from the Institute for Quantum Optics and Quantum Information in Vienna, Austria, and Ian Durham, who's a physicist at St. Elsem College, and also a shout out to the Foundational Questions Institute that funded this research. Okay, so here's how I'm going to break this paper down. It's about the integrated information theory of consciousness, which some of you may have heard of, some of you may not have heard of it. So I'm going to break this down into 4 questions. So first, why care about IIT? The reason why I'm going to start with a why care question is, well, firstly, I think several of you have never heard of this theory. But also, I'm going to be focusing in on some very strange predictions of this theory. So if you've never really heard of it and you're just listening to these strange predictions, you might think this whole talk is bonkers. So I'll start with a why care section, and then I'll move to integrated information theory. What is it exactly? I'll try and define it for you. Then I'll move into these predictions that I'm interested in, which is what is the simplest conscious system predicted by IIT. So this theory of consciousness tells us that consciousness is a measurable physical quantity. That means that it can come in very small amounts. And so we've been interested in what's the minimally conscious system predicted by this theory. And it's not at all straightforward to actually figure out what that is. Then I want to ask the question, can we put that system into a quantum superposition of distinct conscious experiences? Okay, so that might seem like a strange question to ask, but there's a few reasons why I want to ask that question. So, in collaboration with David Chalmers, I've tried to develop the consciousness causes collapse hypothesis. Some of you have, I think, seen us present that in Tucson. So the consciousness collapse hypothesis, which goes back to Eugene Wigner, von Neumann, and so forth, it's sort of still outside the realms of science, mainly because it's not testable. Or at least right now we cannot test it. Despite some of the claims we've seen at this conference, it's not testable as it stands. So David Chalmers and I were interested in how to make it testable. And what we need to make it testable is a theory of consciousness that tells us that consciousness goes beyond just brains and indeed living organisms. If it can tell us that there are minimally conscious systems that are silicon-based, that we can perhaps control and study in the lab, then potentially we can test the consciousness collapse theory with these kinds of systems. So that was one of my major motivations. There's another motivation, which is just by asking this kind of question, we much better understand this theory and we can develop the mathematics, but I won't be talking too much about that part of the paper. Okay, so IIT, why care about it? It's actually by far the most cited theory of consciousness in contemporary scientific literature. So that's just based on how many published papers reference the name in the abstract or the keywords. And actually in the last 20 years, the interest in IIT has been exponential in accordance with this metric. About 5 years ago, it shot past the global workspace theory, which was the second most discussed theory of consciousness in the literature, which is increasing linearly in this respect. And then those two theories are well out in front of all the other theories of consciousness. That does not mean that this theory is plausible or true, especially since I suspect that perhaps over 50% of the papers writing about IIT are criticisms. Still, it's a reason to know about it. It's so often written about, it's worth knowing what this theory is really saying. Secondly, it's one of the few theories of consciousness that has led to technological progress in the science of consciousness. That's somewhat rare. So in particular, it's what motivated the perturbational complexity index measure of consciousness. So this is a way of figuring out whether or not a brain is conscious or not, basically by sometimes called the zap and zip measure of consciousness. So you zap the brain with transcranial magnetic stimulation, you then use EEG to measure the response, and then you use a kind of compressibility algorithm to compress the EEG response. And the more incompressible it is, the more likely it is that the subject is conscious. And in fact, there's a certain value, 0.3. If subjects are above that, they're conscious. If they're below it, they're unconscious. And that's been surprisingly successful as a measure of consciousness, and IIT led to that technology. So that's where it all started in that paper. It also apparently has some empirical support. So you've probably heard about some recent experiments in this regard. So this adversarial collaboration, which just happened, got quite a lot of attention in popular science media, although what you see in the front page is David Chalmers and Christoph Koh, who had this bet on whether or not, 25 years ago they made this bet, whether or not we would have by now been able to isolate the neural correlates of consciousness. And David Chalmers won the bet because he said we wouldn't by now. So these experiments are somewhat inconclusive. They don't establish, I should say, this adversarial collaboration was competing. It was a competition between integrated information theory and global workspace theory. Inconclusive, but by most accounts, the integrated information theory looked a little bit better off. Those experiments were really looking at whether or not the neural correlates of consciousness are in the back of the brain, which is supposedly predicted by IIT, versus the front of the brain, as predicted by the global workspace theory. Whether or not IIT actually predicts that, or actually predicts anything, is a question I want to raise. I'm actually going to raise a challenge to IIT in this talk. Okay, so that's why we should care about IIT. What is it exactly? So it treats consciousness as a measurable quantity, as I said, so it can come in very small amounts for certain simple physical systems. The amount of consciousness in a physical system is its amount of integrated information. That's a measurable physical quantity. I'll say a little bit more in a moment about what exactly that is. You often see it designated with this Greek symbol, capital Phi. So that's half the theory. The other half of the theory is its theory of qualia, or qualitative states. So the qualitative state, or the qualia of a physical system, is given by something called a phi structure. It's gone under different names in the literature. I call it a Q shape, short for qualia shape. So again, I'll come back to that in a moment. Okay, but the theory offers a way of measuring consciousness and a way of representing qualitative states of consciousness. So it does this with a rather elaborate mathematical formalism. This formalism has been updated over the last few years. I'm not sure what 1.0 is, but 2.0, 3.0, and then a few months ago 4.0 was developed and released. And also there's a recent development called quantum integrated information theory, which tries to formulate integrated information theory using the mathematical formalism of quantum mechanics. Okay, so that's what it is. So it's a rather complicated theory. The mathematics is very complicated. The non-mathematical aspects of this theory can fortunately be summed up in a single slide. It's not the simplest slide you've ever seen, but I'm not going to go through all of it. Let me just say a little bit about this table and what it's representing. So IIT starts with a set of axioms. So on the left you've got 6 axioms. These axioms are axioms of experience. They are meant to arise from introspection. You introspect on conscious experience and try to come up with properties that you think are essential to consciousness. Okay, so those are the axioms. And then the thought is, advocates of this theory are basically materialists, or they think that there's a very tight connection between conscious experience and the brain, the physical properties of the brain. And if that's right, and if introspection is at least somewhat accurate with respect to the structure of consciousness, then you can somewhat deduce the structure of the substrate, the physical substrate of consciousness, through this method. So the axioms are figure out some essential properties of consciousness introspectively, and then the postulates on the right are, okay, if the physical substrate is what's generating these conscious experiences that have these essential properties, what must the physical substrate look like in order to generate experience like that? So that's kind of an interesting strategy, a very different strategy to develop a theory of consciousness. I won't go through all of these, but let me just mention a couple. So axiom number 1, consciousness exists. Pretty straightforward. But the move from the axiom to the postulate is quite substantive, and one that I'll focus on a little bit, which is they think existence is really all about causality, causal power. To exist is to be able to do something. So what that means is when they move from these axioms to the postulates, every postulate is described in terms of causality. So axiom number 1, consciousness exists. So what do we then say about the neural correlates or the physical substrate of consciousness? They must have cause-effect power. They must have the power to be cause and to create causes, or create effects, I should say. Okay, I'll just mention a couple more. Intrinsicality axiom. Actually, let me move to information, because that'll be more relevant. The information axiom. So information means consciousness is specific, it is the way it is. That's a summary for, conscious experience is loaded with information. Your experience is packed with information. And so we want to capture that. How do we, in physical terms, capture the fact that conscious experiences carry information? And if we flesh that out in cause-effect terms, in the postulate side, we say the physical substrate of consciousness has specific cause-effect power, and so it must select specific causes and effects. So the physical substrate of consciousness must determine its own later state, how it affects itself. And then there's integration. So the axiom of integration deals with binding, the unitary nature of consciousness, the fact that a conscious experience seems like this unitary whole that's not reducible to individual parts. And then they ask that same question to create the postulate, and that's going to be about causation and information. And so that's where you get the idea of integrated information. Okay, so it's all very metaphorical in that level. You move from the axioms to the postulates, and then from the postulates you get something much more precise, which is the mathematical formalism. And then you meant to apply that to neuroscience, brain data, and then that can help you inform how you formulate these postulates and axioms. Okay, that's the theory. It's a little bit complicated, but to simplify this, I'll just focus on the simplest prediction of this theory. Okay, so I'll bypass a lot of the calculations. This takes about 3 pages of calculations to work this out, but this is the simplest conscious system according to IIT. It's a little feedback dyad. So you've got 2 nodes, A and B. They take on binary states, so they can be 1 or 0, or light or dark, as I've depicted here. They could represent any physical system, often neurons. So A and B could be neurons, and then their binary states could be active and inactive, but they could be anything. They could be tubulin in a microtubule, or they could be electrons. And then in this particular system, we basically represent the nodes as copy gates, so they copy their states to each other. So that's how the system would get represented using the typical IIT diagrams. But we actually had to sort of reframe this because this isn't quite consistent with quantum information theory, and we want to put this system into a quantum superposition of consciousness. So a better representation of the system, which would be more familiar in quantum computation, is to think of it like this. I've got 2 channels instead of my 2 nodes, A and B, and they can take on these binary states, just small a, small b, or 1 or 0, and they are related by a swap gate. So at the moment I've just represented the swap gate by a black box. I'll come back to that in a moment. And then we send the outputs of the system back into the inputs so that we actually have a feedback network. So according to IIT, this is the simplest conscious system. And I'll just say very briefly how they get that result. So it stems from the mathematical formalism of IIT, which itself stemmed from those postulates that I just mentioned. So the system can be in, 4 possible states. So the channels A and B can be in states 0, 0, 1, 0, 0, 1, 1, 1. So if we say that the present state is 1, 0, then that state of the dyad predicts what its future state is going to be and also what its past state was. So the present state contains information about its immediate past and its immediate future. All right? If you understand the rules of the dyad, how it works, and what its present state is, you can infer with certainty what the past state was and what the future state will be. Okay, so there's information in the state of the system about its immediate past and future, and it turns out to be integrated. And the way that you show that it's integrated is by replacing the causal connections from A to B and from B to A with noise that make the later state of each node of the system equiprobable. And then you can show that when you do that, you get information loss. And it's just a way of showing that if you cut the connections in the system, you lose information. You lose self-information, information about the immediate future and immediate past of the system. There are equations for doing this, but it's perhaps a little bit late in the day to take you through the equations, and this is only a small part of it, but if you want to ask me about how it all works formally later, I'd be happy to go through this with you. This, by the way, small phi, the integrated information of A, so one of the components of the system. And so we calculate that just by looking at the probability of the state of B, t plus 1, given the present state, t0 of A, and then we compare that with the noised version. We get a result. It's related. It's a similar kind of equation, yeah. We end up with small phi, integrated information for the two components, A and B, and then to get the phi of the entire system, we add those results, 1 plus 1 equals 2. So the formalism tells us that the dyad has 2 units of integrated information, which translates to 2 units of consciousness. Okay, so I mentioned it also gives a theory not just of the amount of consciousness in the system, so this system has 2 units of consciousness. It also tells us about the qualitative states, or the qualia, associated with any physical system. And basically the way that you calculate that, according to this theory, is you say, okay, my system has a certain amount of integrated information that I've calculated. How did I go about calculating that? So you use certain elements that you use to get the phi to represent the qualia. So just to intuitively get at the difference, you can imagine having 2 different experiences, like an experience of red and an experience of blue. Intuitively, it's the same amount of consciousness. Insofar as we can make sense of this idea of consciousness coming in degrees, there's no reason why the blue experience would have a greater degree of consciousness than the red experience. So those 2 experiences would presumably get equal phi, equal in amount of integrated information, but they're not the same. And so the theory has to represent the difference between the 2, and it's a qualitative difference. And the way it does that, and again, I'm just going to represent this for you without saying too much about the calculations, but I've got Q for qualia. 0, 0 is when A is 0, B is 0. 0, 1 is when A is 0, B is 1. So these are 3 of the 4 possible states of the dyad. And so putting Q around it means this is my mathematical representation of the conscious experience. Now, it just looks like a matrix of numbers. And so you look at that and you think, well, how do I get the qualitative nature of consciousness out of that? So these are sets of probability distributions that each component has over the system's phase space. Okay, it's a little bit complicated, but think of these matrices as being in one-to-one correspondence with all possible conscious experiences. That's fundamentally what the theory tells us. It postulates a one-to-one correspondence between matrices of numbers, which are probability distributions over the system's phase space, and conscious experiences. That by itself isn't going to tell you about the conscious experience of a given system. It's just that the theory tells us that's all you can know from the third person perspective about a conscious experience, because consciousness is subjective. But what you can do, and what I think is quite interesting about this theory, is that you can make comparisons. So you can derive your own Q shapes, your own mathematical structures, and you can map those onto what experience feels like for you, and then you can model similarity relations and deduce what it's like to be a very different physical system, provided that there's some similarity relations. Okay, a lot of these are just mathematical results, so we're able to show that the dyad can be in these 4 possible states. The dyad has the same amount of consciousness in all 4 states, but they are qualitatively distinct conscious states. That just follows from this theory, and you might already think maybe that's an objection to this theory, because how could such a simple system have these experiences? But that's what's predicted by this theory. Okay, so now that I've got that prediction on the table, we want to ask this question: Can we therefore put the system into a quantum superposition of conscious experiences? And the answer is yes, we can do that quite easily. So here's our swap dyad again. So remember, there's just one gate. So this is not meant to be two adjacent gates. There's just one swap gate, but I'm just representing the same thing over time because it's a feedback network. So the way that we superpose the experience of this system, we feed the superposition into channel B. So, this can be any system with a binary state, so maybe it's a photon and maybe 1 and 0 represent polarization states, but it doesn't really matter, it could be anything. So B is going to receive this superposition, while the channel A will just receive bit 0. So we send bit 0 into A, and we send the superposition of 0 and 1 into B. And then at T0, we get this state. And notice we've just got the feedback mechanism going here on the right-hand side, swapping their values. So this state that we've got at the bottom is a quantum superposition of two Q-shapes. So I just showed you that we represent the qualitative state of these experiences with these matrices. This state here on the right is associated with one matrix. This state on the left is associated with another. So according to this theory, that's a quantum superposition of distinct experiences. Okay, so then the next question is, we're still at a very abstract level. Can we actually physically build this in the lab? And we think the answer to that is yes. So here's a simple example. I just drew this on my whiteboard and took a photo, but that's only because I didn't have an optical cable handy, and if I did, I would have put it in this arrangement and taken a photo of it. But this is the system that's going to implement not just consciousness according to this theory, but a quantum superposition of distinct conscious experiences. So A and B are optical cables now. Those are our two channels. Of course, if you look closely, this is one big optical cable. We are able to send some inputs into A and B, but then it's a feedback network. So we put photons into the two channels. So A receives the state 0, B receives the superposition that I just talked about in the previous slide. And then we say, okay, so A's initial photon state, which is 0 in this case, causes B's later photon state. I mean, this is the feedback involved. So under that identification of what causes what, this implements the dyad. Okay, so I know it's a little complicated, but just what we've worked out is this theory, IIT, predicts that this optical cable, which has these two photons whirling around it, is not only conscious, but is in a quantum superposition of distinct conscious experiences. If that sounds crazy to you, then you might want to use that as an objection to IIT, because that's just what it seems to predict. Furthermore, relevant to the consciousness causes collapse hypothesis. So again, in the work with David Chalmers, we used IIT as our criteria for consciousness, because otherwise you can't mathematically formulate a consciousness collapse theory. So we used IIT to formulate a consciousness collapse theory. And so if we take IIT as our criteria for consciousness, then the consciousness collapse theory predicts that this system is unstable. So it is in this state, but that is, according to IIT, a quantum superposition of distinct conscious experiences. According to the consciousness causes collapse hypothesis, superpositions of conscious experiences are unstable, which means the state of this optical cable is not stable, which should be testable. And it would be very, very surprising if we did discover that it was unstable. So that would then be an empirical refutation of consciousness causes collapse using consciousness as the criteria, using IIT as the criteria for consciousness. Okay, you still with me? Let me wrap up. Okay, so conclusions. So the simplest conscious system in IIT is a feedback dyad. It is possible to put the dyad into a superposition of conscious states. Physically implementing the dyad, which is what we did with the optical cable, depends on identifying what really causes what. So that was a key assumption, going back here. The state of A causes the state of B, and vice versa. Now, one way that IIT people might want to get out of this conclusion is by saying, I don't want to describe what causes what like that. And maybe, I think there could well be debate as to whether or not we can correctly say Those are the real causal relationships. But that actually leads to a much bigger problem with IIT, and that's the last point. Physics itself does not tell us what causes what. Physics just gives us dynamical equations of motion that just show us how physical systems evolve continuously over time. We then have to come in and read in what we think causes what. So causal claims is not physics, it's metaphysics. So if I want to apply the IIT calculus to a physical system like this optical cable, I need my physical description of the optical cable, but I also need to know what causes what. IIT doesn't give us that. It assumes that we have it already. In fact, it assumes we get it from physics. But if we don't get that from physics, then where are we going to get it from? And if we don't have a place to get answers as to what causes what, then we don't get a well-defined answer as to whether or not the system has integrated information, in which case the whole theory is not well-defined. And then that leads us back to the first slide, the adversarial collaboration, which was supposed to give support to IIT, because IIT apparently predicts that the back of the brain has lots of integrated information. But that prediction's not valid if we can't map the IIT formalism onto a physical system like the brain. Okay, I'll stop there. Thanks for listening.
We have time for just a couple of quick questions. If I could ask one quick one.
Sure.
On the consciousness causes collapse approach, because consciousness resists superposition, how long does it take to cause the collapse?
That's a good question. So we model this in the way that collapse models usually do it. So take Roger Penrose's collapse model. The speed at which a physical system collapses on the Penrose model is a function of the size of the superposition, right? So the larger the masses in the superposition and the greater the separation, the faster the collapse. Other mass density collapse approaches do the same thing. So for us, the greater the consciousness superposition, the faster the collapse. So that actually is relevant to our example because the theory is probably going to predict a very slow collapse for the optical cable. So if we don't see the optical cable, the quantum state of the optical cable getting destroyed, it's still consistent with the theory insofar as the theory predicts a slow collapse for systems where the conscious states do not differ greatly.
Kelvin, that was an excellent job in defense of something I personally think is indefensible. But let me just say that the axioms and the postulates would apply to any theory, not just IIT. PCI could be mediated by microtubules rather than membranes, so I don't see how that favors IIT. Causality.
Do you want me to answer?
Yeah, go ahead.
Shall I wait? Well, just the PCI. All I wanted to say there was this theory has led to important technological advances. Now, I didn't want to say that we could then use the PCI as empirical confirmation of the theory. I think to get from integrated information as it's mathematically formulated to the perturbational complexity index, that's not straightforward at all. So the only thing is good technology is coming out of this theory. That's the only argument I gave in its favor.
Okay, but it really has nothing to do with IIT per se. It could have been, well, anyway, it doesn't matter. Causality collapses gives you causality. I don't know where else you get real true causality, but you call that metaphysical. I'm not sure why. And finally, if the dyads are conscious, why do you worry? Why are you going to put them in superposition if they're already conscious?
Let me answer the first question. Sure, maybe collapse gives you causation, but IIT needs causation prior to collapse. Because if integrated information causes collapse, we already need some causation in the physical universe in order to get the integrated information in the first place. But that's still metaphysics to say that collapse is causation. After all, collapse theories can be completely well modeled in terms of eternalist block universe models. You can still make sense of the collapse of the wave function in a block universe where there's no causation. What was the second question? If the dyads are already conscious, why are you putting them in superposition? What does that give you? Okay, so there's a couple things. One is to test the consciousness collapse hypothesis. So if I just have this simple system and it's conscious, it doesn't yield any predictions. There's nothing there I can test. What the consciousness collapse hypothesis predicts is that quantum superpositions of consciousness are unstable and collapse. So in order to test the theory, I need to create a quantum superposition of consciousness. That's why I was interested in superposing this system. The related issue is that it's a real test case for the mathematical formalism of IIT, but that's another story.
Well, you know that in our theory, you need superposition which collapses to give you consciousness. So I don't really...
So this is a consciousness causes collapse hypothesis. Yours is a collapse causes consciousness hypothesis.
Right. So I don't understand why you're putting the dyads in superposition.
Because
if
the
they're
theory...
already conscious, you've already achieved what you want.
No. I don't want consciousness in the system. I want it to be in a quantum superposition of consciousness, because that's where I get unique predictions.
It collapses to a conscious system. Since the dyad was conscious in the first place.
It was conscious in the first place. Well, it's in a quantum superposition of consciousness, and then it does collapse to a definite state of consciousness. Okay, but ordinary quantum mechanics does not predict that this system will collapse. The consciousness collapse hypothesis does predict that it will collapse.
Physics predicts that the superposition will collapse. I mean, there's no eternal superpositions that I'm aware of. So why do you need consciousness to cause the collapse? It's going to collapse anyway, whether it's by quantum gravity or decoherence or who knows what. Anyway, I'll shut up now.
Well, I'll quickly there's no experimental evidence whatsoever that wave functions collapse.
There's what?
There's no experimental evidence whatsoever that wave functions collapse. So we don't know if wave functions collapse. That is a speculation. So what we do, what Roger's doing, what we're doing, is we're taking hypotheses about what causes collapse and then trying to detect the implications of the collapse of the wave function. For example, the recent experiments that are looking for spontaneous radiation, which is a signature of certain forms of collapse. Those experiments are in part trying to figure out whether or not wave functions collapse in the first place, because that is unknown.
Right, and they validated Roger's idea, not Diassi's, but that's really another story. So, but anyway, thank you very much.
We're kind of getting out of time. Yeah, we have thanks again.